start that with a story. So where this talk originally came from. I was invited to a longitudinal conference hosted by Greg Hancock and the rest of the folks at the University of Maryland in like 2010. And this was a really big deal because it was like a long list of people that, you know, I was familiar with or I wanted to be included in that set. And so I wrote this talk for that conference. And then a couple of years later, I got an email out of the blue from Joop Hawks, who is a very prominent multi-level modeling guru from the Netherlands. He's written several textbooks on the topic, and he asked if I could give the same talk over in the Netherlands, and he'd pay my way. I'm like, okay, free trip to Europe, where do I sign up? So I went ahead and I was going to give the talk again, and he introduced me. And so I was like, okay, what's he going to say about me? And what he said was, I had to teach a longitudinal class for the first time and I didn't have any material. So I started Googling like how to teach longitudinal, and he found my stuff. And on the basis of my teaching materials, I got a free invite to Europe to present at his conference. So anyone who says that teaching doesn't really matter, it's all about research, I don't know about that. I got a free trip to Europe. And we got to go to Paris at the same time, and that was a lot of fun. So the knowing stats, beyond just making you better at your research, can literally take you places. If you can make yourself a reputation for being an accessible presenter, having all my stuff online, I think, helps people know what they're going to get in advance. That, you know, it's like try before you buy. So because of the teaching that I did, I got a chance to go and do this. So this is an example of a presentation that I would give at a conference. So the slides are slightly less wordy than my typical slides, but not by much, of course, because I kind of want things to stand alone. And I looked this over, and it was interesting because my perspective on this topic has changed a little bit in recent years. And so the handout that I developed to go with this set of ideas is brand spanking new. I literally just finished it this morning, as I told you over email. And there's stuff in it that I didn't know when I wrote any of this or when I wrote chapter 10 in the textbook about it. And that's the end of it that I'm excited to be able to start to continuing develop what I know. So that's the story about the talk. Do you want to hear it? Why not, right? We're all here. So this is my talk. It was supposed to be about 45 minutes, but if I keep telling stories in the middle of my slides, it will go a little bit longer, as I'm prone to do. All right, let me get the screen share going so the Zoomers can see what I see. There we go. Zoomers, can you see my red slides? Do you know why they're not yellow? Because I wrote this when I worked at Nebraska. If you see other talk slides that are blue, I wrote that when I worked at KU. So I tend to use the slide colors that go with wherever I've worked, although it's not like the officially sanctioned colors. I picked the ones that I liked a little bit better. But all right, so away we go. This is 10 years old now, my goodness. So there have been, in the past, a lot of work describing, you know, strategies for longitudinal analysis, steps of longitudinal analysis, concerns, however you want to think about it. Here's at least 3 different places where people outline sort of what's the purpose and how do you go about doing it. And I have a note here that everything I have to say is agnostic as to whether this is from a multi-level modeling perspective or from an SEM perspective. It's a longitudinal model either way. So I have my own list of steps then. Step 1 is always to decompose between versus within person variation. Yes, thanks for the prompt about the recording. I am recording, so it does count. Otherwise, I'd have to like re-give the talk yet again. Intra-class correlation. How much of your data is actually longitudinal? That's always step 1. And how much of the data in this context is actually due to cross-sectional differences that was there to begin with? That's an important question, not just for any outcome, but also for with respect to time in analyzing change over time. Then we have step 3, see foreshadowing, I deliberately skipped step 2. Describe the pattern of average change, that's what fixed effects are for, and individual differences in those tendencies for random effects. And there's lots of different ways that people have gone about this. We can do piecewise models for discontinuous phases of change. Polynomial models, of course, are very standard, even though they are a little bit, I would say, less theoretically appealing. unless you're studying a phenomenon that goes up and then comes back down, or vice versa. Truly nonlinear models, where we're looking at things like exponential or logistic change, and then also latent basis models where we don't try to a priori figure out what pattern it is, we let the data decide, and we estimate factor loadings that provide information about the shape. We're going to do that next week, by the way. Step 4 then would be to predict inter-individual differences in change. So why do people differ from each other with respect to their random effects, their intercepts, and their slopes for time? Step 5 is predicting intra-individual variation. So why are you off your line today is the way that I always describe this. What is going on beyond your stable tendencies that contribute to time-specific fluctuations? Multivariate relationships. So how do the intercepts and slopes across different variables relate to each other? If somebody tends to start out high on this outcome, do they start out high on this other outcome too? If someone changes more than everyone else on this outcome, do they also change more than everyone else on a different one? And those can be phrased as associations, like correlations, or they can be phrased as regression paths. The latter requires SEM-type software. Within this flavor is also what I call lead-lag associations. So the idea of like this times X is going to predict next times Y, and this times Y is going to predict next times X, that kind of thing. This is the gesture I always make with that. And then because when I wrote this talk, there was a whole section on mixture models at the end of the conference, I threw in number 7 because I was trying to play nice, even though I think mixture models are mostly bullshit. Didn't say that part out loud. Mixture models for discrete types of individual differences. So this is the idea of trying to find hidden groups of people who have similar trajectories. Those are exploratory models in almost every case, and that's my problem with them. The same problem that I have with exploratory factor analysis I have with mixture models. So the missing step 2 then. What haven't I covered? And to me, it comes right after intra-class correlation, is what should time be? So when we talk about modeling change over time on average and individual differences in change over time, we are presupposing that we know exactly what time is. There's a lot of sampling designs and research questions, though, where it's not necessarily clear what time should be. So it's 2 different concerns. First, what should time be? And to the extent that people walk in the door at a different point in that time, how do we address those between person differences? So when this is relevant is in a particular type of study design that's known as an accelerated design. Synonyms for this also include cohort sequential designs or overlapping cohort designs. And it's the idea that you want to do a longitudinal study, but you want to do it on the cheap. You don't want to follow people for as long as it would take to show all the changes. You want to sample people at different points and overlap them such that together they form a coherent trajectory. In other words, if I have a design where each decade of people is sampled for 10 years, I can hopefully piece those separate groups of people together so that I can talk about age-related change from age 50 to 95, even though not a single person was measured for 45 years in a row. That's the logic here. This is a reasonable thing to do if you're in a situation where the people that you're seeing or studying are mostly the same. So like the 4-year-olds, right? If you're sampling 4-year-olds this year and you have another group of 4-year-olds that you see next year, do you expect the 4-year-olds to be much different from each other? Probably not. But what about a kindergarten cohort who went to kindergarten on Zoom in 2020 versus a kindergarten cohort in 2019 who hadn't learned the word pandemic yet? Might they be different? Quite possibly. So the problem comes in when people differ from each other for other reasons besides time. Then this nice trajectory where everybody aligns isn't going to work. So the missing step 2 then, what should time be? What is the metric of time that best matches the causal process of time? That would be your starting point. Then evaluating the extent to which maybe you're wrong. Do alternative metrics of time that cover multiple different processes create different trajectories? And how do we align people is really the question. Within persons, time is just time. We're 1 year further from birth, we're 1 year closer to death, we're 1 year further in the PhD program, we're 1 year away from graduation, right? Like, it's just time marches on. So it's not a distinction that's relevant within persons, but it's relevant between persons. So then how do we model time? So I had given a couple examples at this point in the talk that were temporally relevant. They're no longer relevant as much, but I'm going to give them anyway. One is this idea of age. So if I go back to this overlapping cohort, if this design works and there's nothing different about people other than the age they currently are, then I should be able to look at the time I was about 35 and say that I should be able to look at my grandmother, Mimi, to see what age 80 is going to look like for me. Even though Mimi, by the time she was 35, had given birth to 7 children, and I had none. She had never went to college, and I have a PhD. She spent most of her time sewing and cooking, and yeah, I can't do any of those things. And up until fairly recently, Mimi never owned a pair of pants because ladies wore skirts. I think I might own a dress, and I'm pretty sure it's packed in the box that I threw it in when we moved to Iowa 4 years ago. That tells you anything about how often I wear dresses. So despite like all of these things, right, I should be able to be like, this is 35, this is what 80 looks like. My 80 is not going to look like Mimi's 80 for a variety of reasons that have nothing to do with how old she is and everything to do with the life that she had and the experiences that she had. The other example that I can give with this is the quest for tenure. So I know all of you are at the comp stage and the dissertation stage and the employment stage, but eventually, if you're in an academic setting, you're going to have to go hop on the tenure ride. And when I went up for tenure at the University of Nebraska, I was in psychology, not a clinician as well. It's okay. We don't all have to be clinicians. I was one of 4 people who were going up at the same time. And what made our cases interesting is, where do you start counting when it comes time to evaluate your productivity for tenure? There was one of us who not only had a postdoc, but also had a 5-year K award before he started his position. So he had like 8 years of research experience beyond the PhD. There were 2 of us, myself and one of my colleagues, who had standard postdoc 2 to 3 year appointments before we started our jobs. And there was one person who came here straight out of PhD from Iowa, your guys' department. I believe her name is Ann Shuddy. You might have heard of her, but it's a small world, so I mentioned that. So she started like she graduated, and then like the next day was a professor. Now, I don't think it's a reasonable thing to expect all 4 of us to have the same level of like total publications, because it's like, where do you start counting from? Some of us had a head start. Some of us had a bigger head start. And even if you're like, well, you started in 2006, and so that's where we're going to count. The things that were published in 2006 were stuff I wrote in 2003. Like, I still had a head start, even if you can't you set the clock there. And once you're part of a research lab, you have momentum and you have projects and things that are moving along that's just different than when you have to start your very own lab and get that off the ground. So like, what should time be in clocking tenure? There isn't a fair way to go about deciding it. Ultimately, the 4 of us were all successful, but you can envision that there could have been some debate as to, whether it's fair to expect the same level of productivity given such different levels of preparation. So, point is, this shows up in, I think, more context than is immediately visible in the world. And so I want to put this in your head in terms of like, how do you think about time and how do people differ from each other in the time metric of interest? The context of this presentation is actually a little more depressing. It's about older adults who are experiencing cognitive decline, but the question is, cognitive decline as a function of what? So, any questions so far?
Yeah, in designs like this, you were talking about how like you would want them to be similar. So I'm curious what like a sampling strategy might look like if you wanted to do something like that.
Well, I think that this is kind of a recipe for disaster if you're trying to piece together 40 years.
Yeah.
I think that, like, in the context of, say, elementary or high school education, sampling from the same school repeatedly, as opposed to going to different schools, for instance, that would help control some of the extraneous differences. Collecting information about anything that would have happened that has to do with the stuff you're studying. So, like, if you're studying, alcohol and drug use in teenagers, and in one cohort there's a new, don't do drugs initiative or something that popped up just all of a sudden this academic year, maybe that matters, but it's a testable hypothesis if you know when that popped up and for whom. Same thing with things where, like, if teachers are going through new trainings and whatnot that are supposed to improve their teaching, and the new cohort got the teachers in the trained version and the old cohort didn't, like anything like that that you can keep track of and try to control for will help you. But ideally you'd want the chunks here, the cohorts, to be as homogeneous as possible. And that gets harder and harder to do the further you stretch it. So,
Thank you.
yeah, it's not a good answer. I'm going to level with you, but it's the only answer I got.
Do the 40-year study is what you're saying.
Well, so that did happen. There is a study, the Seattle Longitudinal Study, started out as Warner Shia's dissertation in 1956, and he collected information from these people every 7 years until he has to be dead by now, but I'm not for sure that he is, like, until like the 90s. Like, it was a 40-year study. And then they got, like, the offspring of the original participants and the grandchildren, and they have, like, a whole genetic arm, and it was like a whole thing. But that was his career, right? To do a 45-year study is one's career. So if you really want to study adult development, but then, like, it would be this cohort of 50-year-olds, right? The people who were that age in 1956 is who he can generalize to. So that's also somewhat limited, in the same way that Mimi and I are not the same. Mimi is dead, by the way. She did die a couple of years after that, but great cookies. That's what I can say. Solid. Okay, you had a question. Did you have a question? Or does someone else have a question?
Yeah.
Okay, you and Daniel.
Something that's a little bit more common in my area of research is, like, people using different samples of students, like, over semesters. And then I guess it's not quite I guess my question is whether that's actually similar if they're just aggregating across different semesters and not trying to get, as you say, a wider span of time than would be available. Like, that's not relevant to this, right? Unless they try to track change over 32 weeks of data, for example. It's 2 semesters.
It's another example of trying to link cohorts together to get a picture that's wider than any one cohort can do. It's not quite the same, though, but that type of design, so the question was, like, if you have a sample of students in a particular class, and for someone who teaches the class repeatedly, you have, like, the fall cohort, the spring cohort, da-da-da-da-da. There are people who would try to do a longitudinal model on the aggregate of that student level information, because it represents, like, the teacher in that. It's like the teacher's being followed longitudinally, but it's with different kids over time. There's also a bunch of research like that so ICPSR, I used to teach workshops for them, and they had a lot of designs where countries were followed longitudinally, except the way that they were followed was different people at each occasion. It was people nested in occasions, nested in countries. And they wanted to make the argument that they were doing country longitudinal analysis. And I'm like, ew, that makes me really squishy. Because you'd have to have an outstanding sampling design to be able to say, the only reason that this answer differed in this time from this time, it's not the people, it's the time. And I don't know about you, but as long as people can not participate in research if they choose, I don't know how you'd ever get, like, a perfectly representative sample. There was one country, and I don't remember which one it was, but they said that in order to get, like benefits, like, they had to participate in research to some extent or something. Like, so they had, it was like mandatory information collecting. So they were motivated then. But short of having that level of control, I don't know how you do it. So it is relevant, but not quite the same, I would say. I would tread carefully in that case as well. Okay, did you have a question?
Yeah, for the same issue, for similarity or homogeneity, so could we choose one of the variables and check whether it is homogeneous across all those chunks or groups? Is that like a valid idea?
How would you define homogeneous? If you're trying, so the question was, can we take a variable and figure out if it's homogeneous across all of the cohorts here?
With a statistical test like Levene's test, for example.
Well, equal variances, equal
Yeah.
means, is that? Yeah, so the tricky part is that you might assume that someone who's 95 has a lower outcome than someone who's 50. But the question is, like, is this the same 95-year-old outcome you would expect from someone who's 50 versus someone who was still around to start the study at 85? Like, think of it as a missing data problem. Who is left to start the study at 85? The super seniors, right? The ones who've made it that far, who are cognitively and physically capable of participating in research. So it's a question of like not just the homogeneity of like the result of the data, but of the sampling process that would have gotten you to those cohorts. In this case, the people who would be the lowest are selectively going to be removed from the population. So it gets much trickier in an aging context. It might be easier in like a classroom context or something where it's more standardized. But we're lacking the information that we would need to say, like, does this box here, do they have the same value at 50 as the people who are 50 right now? Like, we don't have the counterfactual of what would have happened had we followed everybody the whole time, that you would need to really, I think, nail that down. Okay. Other thoughts, questions? All right, moving on then. Yeah, so here's my example. So as a postdoc, I had access to a very rich data set. I've used this data set in a number of places throughout my examples. Octogenarian twin study of aging. This was a long-term study conducted in Sweden. They sampled people starting around, the youngest participant at the beginning was 79 and some change, all the way up to 80 at the first occasion. So it's a study of the oldest old, and not just the oldest old, same-sex twin pairs specifically, because they were looking at the genetic components of aging and whether if your twin got dementia, are you more likely to get dementia, and all that kind of stuff too. In this data set, everyone has a known date of birth. Everyone has a known date of death because they followed basically the records of the folks long enough to figure that out. And I selected from the original sample of 600 and some odd people, 173 persons who had an estimated date of dementia diagnosis. So there were different kinds, Alzheimer's type, vascular, or like unknown mixed origin, basically. These are the things. So these are estimated, right? Because we don't know when dementia happens to somebody. We see evidence of cognitive decline, and we work backwards to try and figure out when it must have started. But dementia is bad for you, just in case you didn't know. That's all you need to know about like cognitive aging. Dementia is not good. So then the question is, what is the right metric of time here? Is it how old they are? Is it, so I think of that as years since birth. Is it how much time they have left, which is years until death, which is a very morbid topic, but it actually does work much better in this type of situation, or years to diagnosis. So there were a few people who were like going to die like the next day after they were measured. Like it was really, really close. And some people that kept going long after the study was concluded. It happened over 8 years. So this is the correlation amongst these three variables at wave 1, how related they are. So the strongest correlation is between years to death and years to dementia diagnosis, but it's only 0.5. So it's not like a life sentence if you have a diagnosis that you're immediately going to have, some other outcome happen to you. I have 3 outcomes that I'm looking at. I T-scored them, which is a standardization to a mean of 50, standard deviation of 10. I did that to put them onto the same scale and to make the numbers big enough to where you could see differences in the coefficients. Like you could Z-score or make up some other metric, but I just chose that one for that reason. So we're looking at 3 different things. Mini-mental status exam is a test that is used to screen for dementia. So this is, in a sense, like the rightest answer that we can have in real data because they would have been diagnosed using this test. Object recall as a measure of memory, and then spatial reasoning block design test. So these are fairly standard kinds of measures. So then, what are my possible metrics of time and their interclass correlations? So we haven't done this yet, because it hasn't been relevant. Question from the Zoomers. Years to death. If someone passed, would the years go forward or would it be positive or would it be moving backwards? It's backwards. So it's years to death is on the negative side, where 0 is the date of your death. So up to 16 years.
Like a session, so like if someone died, let's say on the second session,
Mhm.
so it would be like -1 and then 0. Moving forward, would that person be like 0, 0, 0, 0, or would it be like +1 year after that, +2 2 years after that?
So in this case, they wouldn't have any outcomes when they're dead, so there's no more data.
Okay, so then they just like would drop out.
Yeah, so they wouldn't have any more rows. Like the highest they could be is 0, because then they're dead. And actually, when I first got the data set, there were some dead people who had cognitive scores in it. That was one of the cleaning things that I had to do, was to figure out, like, if you're dead, how did you do so well on this test?
Maybe that's the key.
Yeah, it's like, that's an odd problem to have when dead people are performing well, or at all. But yes, so 0 is the highest value then in that particular time metric, whereas since birth is only positive, right? Because 0 is when you were born. And then diagnosis is both positive and negative if there had some time before it and then they were followed after it happened. So we can actually compute intra-class correlations for these metrics of time as a predictor, which is not something we've had to do before, because I deliberately withheld all of this complexity from you in the previous class. The time metric that we used is time and steady, which is balanced across persons in all of the examples I did last semester, and means there's no between-person variation. So it's a purely level 1 variable. That way, when we talk about fixed effective time, it's a purely within-person effect. Then we have between-person slope differences and within-person slopes of time. So it's all nice and tidy. This is where it gets messy, because we're mushing things together, essentially. So if I take age and I fit it as an outcome in an empty model, in this data set, the intra-class correlation was 0.47. So about half of the information for change over time was actually age differences cross-sectionally. Some people were older at the first occasion, 80 to 100, and then followed for up to 8 years.
Sorry, just to make sure I'm following. You said you put age as the outcome.
Yes.
Great.
I model age as an outcome so that I can partition its variance into random intercept level 2 cross-sectional mean differences and level 1 residual within person.
Great.
Yep. So the point is that if I want to talk about like change as a function of age, half of my change, like the information in this variable, only half of it is about change. The other half is about pre-existing age differences that were already there. And my model has to recognize that those are two different things. Likewise, years to death, 24% between. And dementia, 70% between. And then as a point of comparison, time, 0. Time and steady. Basically, 0 is when you got here, how long has it been? And in this case, it's 2 years, 4 years, 6 years, 8 years, with a little bit of wiggle around that. So it's a little bit unbalanced, but not in a significant way, I would say. So these are my choices. Then I made some pictures. I made these pictures in SAS a very long time ago. I don't know how to make these pictures in any other program. How I made these pictures is, this is what people colloquially call spaghetti plots, or plots of individual trajectories. The name spaghetti plot gets its name because if you took like a handful of spaghetti and threw it at the wall, like this is what you would get. But then I saved the means from a saturated means model as a person in the data set and then made their line look like this. So it's a mean trajectory with people in the background. I'm sure you could do this in any other package, I just don't have the skills to do so. There. So if you look at the fit of the average lines to the trajectories, let's look at this top one here. How well do you think this fits? Does the slope of the line look like it matches? No, it looks a lot more gradual. What I see is cliff, 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 like fine, not fine. Whereas this is like doo-doo-doo, just slowing down. This one's a little better, but still, like, it looks like a more gradual change on average than what any individual is doing. This one arguably is the best match. as well it should be, because this is Mini Mental Status, the test that's used to diagnose dementia. Like, you should get this right. And so it does match reasonably well, except for this part right here. And again, if you think about who is still participating in research 4 years after diagnosis, the people who are doing the best, everyone else is not participating anymore or is no longer with us. And then time and study, the last one here. So this one also doesn't look like it matches that well. And there's a lot more heterogeneity in the y-axis because this is an agnostic time metric. It doesn't presuppose what's causing it. This is where you were, this is where you are now. Here's object recall. Arguably the same trends, although not quite as pronounced, since this is not tied to diagnosis specifically, but the age trajectories, and this, by the way, is a predicted mean that's going outside the scale of the data. Because a saturated means model returns the means that would have been there in theory if the data were complete. And it actually predicts it goes below the floor of the measure. Because who's still around at 94? The super people. So same problem with going outside of bounds for some of these other metrics as well. And then spatial reasoning, similar patterns here. On average, change looks a lot more gradual than it does for any individual. So the most common approach to this type of data, and indeed the approach that I had been reading about in a bunch of papers when I was working on this and learning about cognitive aging in graduate school, is to fit what I call an age as time model. So this is an example of a quadratic model. So I have age minus 84 because that was near the mean age at the beginning. So if we don't center age, we will end up with predictions for newborns, which will cause convergence problems and nonsense. And I have age squared here as well. And so then I have the fixed effects in the first column here, which describe what happens on average. So this would be the predicted outcome for any of my measures at age 84 specifically. The linear slope is the rate of change at 84 because it's conditional on this one. And this, of course, because even 10 years ago I had this right, it's half the rate of change, which is why we have to multiply it by 2. And then the random effects over here as well. So this model seems reasonable, but it's making a very strong assumption. It's making an assumption that is called age convergence. Another way of saying this is that we're assuming that younger and older people differ only by age. There's no like me versus me or pandemic cohort versus not. There's none of that. Just the reason this person is doing worse is because they're older, the end. Another way of saying that is that the effects of cross-sectional age differences that were there at the start are of the same magnitude as within-person longitudinal age changes. It is the exact same problem that I call smushing as a phenomenon. If you've read chapter 8 or 9 of my book yet, that's going to be one of our next units, as failing to separate the between and within-person effects of any time-varying predictor. And the 2 talks ahead of me were about this at the conference, and so they'd already explained all of that, and I knew that, so I was able to not have to explain it. Otherwise, that would have been another half hour of this talk tacked onto there. So when you're preparing your presentations for conferences, see who's going ahead of you, and you can probably save some space because they would have already explained some of the stuff if you're together in a coherent session like this. So in my case, Patrick Curran, I had already explained all of this, and so I just got to say this sentence and do that. So age convergence then is not likely to hold when the initial range of age is large, such as half the variation in this case, or cohort and selection effects are large as well. So what would this look like then? We can use a variant of grand mean centering, as we have done with our level 1 predictor, to test this empirically. And this is going to sound crazy, but we put in age twice. We leave time-varying age in the level 1 model, and then we put in age at baseline as a time invariant predictor, also centered at 84. Now this seems like it should be redundant, right? Because it's age twice, but this is a within-person constant, and this one is a within-person variable. So if it only matters, that's your 84. These 3 fixed effects should be 0. if it matters when you were 84, if not all 84-year-olds look alike, then the age you were when you walked in the door should carry an additional contribution. So this forms what is called a contextual effect rather than a between effect, because it's an increment beyond the, after controlling for what age you currently are. And I had noted that these are contextual effects with respect to the fixed effects only, which is the new part that I learned about within the last year or two. So we're controlling for basically these fixed effects of time-varying age by adding fixed effects of time-invariant age, but we are not yet controlling the random slopes, which is the problem. Yes.
Two questions. First of all, could we test cross-level interactions between these two slopes, the level 1 and level 2 time slopes?
I just did.
Those are the cross-level interactions. Okay.
So this one is a main effective age. So that would allow the intercept, which is your expected value at 84, to differ based on where you were when you walked in the door. This allows your linear slope, and this allows your quadratic slope to differ.
Great. The second one is, so the other way to create contextual effects would be via random slopes?
Yeah, that's what is actually needed here. That I knew that it wasn't the same. There's like slides about this coming, but I knew it wasn't right, but I couldn't figure out why. And now I know why, because Jason Reitz and Sonia Sturber published a paper on it. They presented a talk about it at SMEP like 2 or 3 years ago, and I lost my mind. I was like, what? You can smush a random effect? But in hindsight, it made total sense. So I give them credit to figuring this out, because he did the math on all of it. But this is an application that I don't think they've tackled yet, that I've been talking about this for 10 years. And so to like have it resolved is very pleasing to me.
Lisa?
Yeah.
What would be the interpretation? So, because in this case, for the fixed effect, would be something like if the person mean matters beyond the individual age.
Mm-hmm.
But what about the random effect in that case?
Well, I'm going to save that question, because I need some equations to answer that question, and they're coming in like maybe 12 slides or so.
Okay.
There's another pro tip. So I have a slide number here. Note that there's no denominator. Never tell your audience how many are left. They don't want to know.
Says the person with 70 decks left.
I know, right? Can you imagine how demoralizing that would be if you're like 12 out of 75? Like, you know there's 75, but you also don't have the expectation that I'm going to get through 75 slides in a 45-minute time block. Right? It's 1:21, and I'll get through as many slides as I get through, right? It's my show. Do what I want. So, yeah. So, let me show you a picture, okay?
Yeah,
Go ahead.
yes. First of all, so in this case, if we are not including random slopes for the level 1 predictors, those are systematically varying effect?
Yes, they would be.
Okay.
Yeah, without these U's, then we would say that these time-varying age slopes are systematically varying as a function of baseline age, but not random otherwise.
Great. Great.
Yes, and so this is a point. I'm using age at the first occasion as my indicator of which cohort you're from, because everybody, all the data were collected in the same chronological year, so that's the same thing as saying birth year. But if you had a study that was over multiple years, this should be something like birth year instead as your indicator of cohort. I could have picked the person mean age, which is the more traditional way of doing this type of modeling. However, in this data set, there's a bunch of missing data. Not everybody was around for 8 years, as you might imagine. So what I wanted to avoid was a situation in which it looked like somebody was from an older cohort because they had more data than someone else who was born at the same time but had less data. Because if you go the whole time, your mean age is higher than if you only show up once or twice. And I didn't want that to mess this up. So I made a choice to use age at the first occasion as my indicator for like which box you're from, to sort of simplify that. So I'm thinking of this as a purely cross-sectional variable, and then hopefully what's left is supposed to be longitudinal. Now it's easier to explain what this model is doing in pictures. So here's an age convergence model. This is what a trajectory would look like. This is for a mini mental status exam, the diagnostic of dementia. for the model without these things, so just this one, without that, okay? That line came from that model. No cohort effects. So this is assuming that regardless of when you started, here's the expected quadratic trajectory. As you can imagine, it's a negative decline that appears to be accelerating as people get older. So a negative linear paired with a negative quadratic. This is what it actually is. So this is, I want to say maybe 4 years different. So I picked somebody who started at like 80 and somebody who started at, no, 6 years different, at 86. And I generated predicted outcomes based on the model that had age at time 1 as a moderator of the intercept in both slopes. So in the age-based model, the intercept is at 84. That's when all the predictors are 0. So this then is the intercept. This is the expected trajectory for the 8 years of somebody who started at 80. This is the expected trajectory for the 8 years of somebody who started at 86. They don't align. And if you follow this line back, like if you extrapolate like what the model would say, the older cohorts are actually higher at the intercept, which is counterintuitive. People who started older did better when they were 84 than people who started younger. People who started older did better at 84, according to the model, than people who started younger. Now, why would that be? These are real data, so I can't fully know, but I will take selection effects for 1,000, Alex. Who is left to begin a research study at 86? The super seniors. Are they a random subsample of all the people who were around at 80? No, they are not. So as the population like gets older, the bottom kind of goes away, and you end up with this drift where people who are older are actually performing better because it's not the same people, it's the best people in terms of their potential, their capacity for performance. So this is what actually happens. There is a cohort effect. The clumps don't align in this particular data set. Moreover, the older you are, the steeper your decline as well. So the rate of change depends on where you started, because the rate of change covers a different time period based on where you started. Here's what it looks like for object recall. So this is a quadratic where we have a negative linear paired with a positive quadratic, so it's kind of slowing down. That's probably because this is the floor of the measure, so it can't go much lower. And yes, I totally ignored that. I already got that question from Vladimir. Shouldn't this be a generalized model? Yes, but this is hard enough. So forgive me for not like doing all the rightest things at the same time. Sometimes you got to make choices, right? So we're just forget about that. Here's object recall. Same thing here, basically in terms of a positive cohort effect and a different slope. And here's spatial reasoning. Same type of trend here. So the older cohorts, the older you are when you start, the better off you are. Another question from the Zoomers. Why was 86 chosen for the start of the second line instead of 85 or 87? There is no reason. The model predicts outcomes for any range of age that's at the start and any range of age in time varying. So I just picked sort of like prototypes to show. I'm not dividing up the cohorts. I'm treating age as a continuous variable. I just happen to show a line for someone who started at 80 and 86. The study went every 2 years, so that's another factor. I stuck with even numbers just to make it make sense on that. So if age is just a time varying predictor, then here's 2 other alternatives. What if it's not about age? What if age ain't nothing but a number? What if it's about what is known as terminal decline, or processes that take over and lead to one's death? Or dementia diagnosis, which is a very specific process that causes decline. Well, if it matters when you were 7 years prior to death, which is my centering point, or if it matters how, when you were diagnosed, when you were at diagnosis, then that's a cohort difference. So I can substitute these versions of time into the same equations and make the same pictures. And in this case, they overlap much better. Now, this is mini mental status, which is used to diagnose it, so it's better. But even for years to death, it's much closer. Here's what it looks like for object recall. So much closer alignment as a function of how much time you have left, not how old you are to begin with. Same thing with spatial reasoning. So these, on the face of it, look like they do a better job than just age.
Are those?
Yep.
Are you going to show the equations? Is I guess the first question.
So
Okay.
the equations would be the same as this, just swapping out what
Okay, so
the
you did-
predictors are.
Put in the equivalent of age at time 1 for death and diagnosis.
Yep, years to death at time 1, and then years to diagnosis at time 1 as my indicator of cohort. And for those metrics, it looked more like those things were not needed. There was much better alignment. Like, it didn't matter, like, somebody who started 7 years to death versus 3 years to death, like, they were at the same point, like, by the time they were 1 year. Like, it didn't matter where you picked up, everybody's kind of on the same trajectory.
Which is what we're trying to achieve.
Which is, yeah, this,
Okay.
that would be, like, that's a sign of a well-fitting model, I think, in terms of, like, you've identified the causal process if it doesn't, like, if it doesn't matter when you were at that point in the process.
Yep.
This
Okay.
is real data, and I can't cause anything, but, you know, like, theoretically. If you need all of this machinery, like, age is not the right fit to this, if it doesn't match up, would be my argument. Comparing,
Lisa,
go ahead.
sorry, just real
Go ahead.
quick. So like, that's what you're showing on slide 20, with how those lines are completely different. You're showing that this is not a good model for this because of these differences.
yeah, so if age is really the story, then it shouldn't matter how, like, when you were 84 shouldn't affect anything, but it does.
Okay, that clears up my prior question too. Thank you.
Yeah, so like this line over here says that the effect of being an older person and the effect of getting older are the same thing. And that's not true. Otherwise, it would align once given the chance. Getting older and being older are not the same. That's the take-home message here.
And all of this is because we're trying to figure out which metric of time we want to use. So hypothetically in a study, I don't know, where you have 20 years of data and almost 9,000 observations,
Hypothetically.
hypothetically measured yearly due to federal reporting requirements, you wouldn't necessarily need to do this because time is year.
In your hypothetical case, if everybody, like, if 2005 was like year 0 and that was true for everybody, you don't need to worry about this. But if you're trying to string, like, times together in a way, then you do need to worry about this.
Okay, I'll chat with you a little bit later.
Okay. Where I'm going, actually, I'll just tell you the punchline now so that you can, like, we'll do some foreshadowing. All of this is stupid and you should just use time. That's your punchline. And I will show you why. Probably not today, we'll make it there tomorrow. But maybe today, let's see. Comparing models by fit. So here's AIC and BIC of each of these alternative ways of clocking time: age, time since birth, time to death, or time since diagnosis. In AIC and BIC, which is better, bigger or smaller? Smaller. Always. It doesn't matter whether your program gives you -2 times the log likelihood or log likelihood. AIC and BIC always has -2 log likelihood as its starting ingredient. So smaller is always better. So who wins? Time to dementia, for at least in most cases. We could also look at the size of the variances left over. So residual variance, how well did the within-person information get accounted for by time-varying age, time-varying years to diagnosis, time-varying death? It looks like residual variance is also lower for the informative dementia metrics in death than age. Intercept variance, also more striking. So the argument that I made with this is that if the time metric is, like, theoretically, like, causally informative, you should see a minimal amount of between-person differences. The fact that there's so much more variance at the same age means the age isn't, like, the story here. That's my argument. People shouldn't differ from each other as much if you've got the right, if you've aligned them properly across their trajectories. And then I said compare models by data, just look at it. Right, like this does not look good. I don't need any stats to tell me that. It doesn't match. This matches better. So there is a difference that the overall model is not capturing until you pay attention to when each of these lines started falling down. All right, so what about just time? So when you're in a situation of non-convergence, when the cohorts don't overlap, an alternative way of setting up the model is probably going to be more useful and intuitive. Time and steady. 0 means you walked in the door, and we keep track of how long it's been since then, the end. So another way of saying this is that time is time varying age minus age at baseline. So time varying age is a column, minus age at baseline is how you make time. How long has it been since you got here? So we're stripping off all of the between-person information with respect to age, and we're focusing purely on the longitudinal information that each person brings. So, yeah, go ahead.
So, sorry, that stripping off of the between-person variation, is that a consequence of what we're doing, or?
It is another way of setting up the variables. It is the alternative that I recommend.
But it doesn't forcefully reduce all between-person variation, it just happens to help do that class, right?
Say that question again.
So it doesn't necessarily bring the between-person variation down to 0.
It doesn't, it removes the between-person variation from the level 1 model, is what it does. And we're going to put it up in the level 2 model where it belongs, is the idea. So we're starting without an assumption that everyone should align. We're changing it to just be, what is your slope? And then we can predict why it is that some people start out higher or lower. Is it because they're older? Is it because they are closer to death or closer to diagnosis? Then it turns into a testable hypothesis as to how do you arrange people and what matters between persons. So to show this idea of the stripping off, so let's say that we have a column that looks like this for age. So we have 2 people who started at 80, someone who started at 84, etc. So the age variable as time is age that's time varying, so the TI subscript, minus age at time 1. That creates a column that looks like this, and then we keep age at time 1 over here. So age at time 1 is a constant for somebody, and then this is the variable part. Well, what if we did this for years to death? Let's say this person started at 12 years to death and someone else started at 8 years to death. We do the same thing, save their years to death at time 1 as its own column, and then we have within person years to death. Looks suspiciously similar, doesn't it? Within persons, it doesn't matter because you've stripped off all the ways that people differ from each other to start with, and it's just time. So the next set of slides are here for brief story, and then we'll pick them up next time. The next set of slides are solely motivated by my desire to show someone else that they are wrong. Okay, that's the story behind this. Because when I was a postdoc, I was in the world of cognitive aging, working with Scott Hofer at Penn State University, Marty Slawinski at Syracuse University, learning how to do growth models and fitting them to these kinds of data where these are the sorts of designs we were working with. And there was another scholar, his name was Jack McArdle. He is no longer with us. He used to write in papers that it didn't make any sense to have time as your level 1 metric because it wasn't a developmental study. It wasn't a developmental model, and he wanted developmental models, and it had to be age. So not only was it like wrong from a stats perspective, it was wrong from a theoretical perspective. And so that, I was like, no, because math don't care. I almost had to borrow Jonathan's mug today where I got him that says math don't care on it. Because no, I can show you the algebra that proves and this is the only time I get to use this word, proves that these models are the same. I can start with an age-based model, and I can start with a time and study model, and I can rearrange them into the same. So the difference is that once you control for age at baseline on the intercept, whether you have age as your time 1 metric or time, you get the same within-person slope. The difference is in how you get there. So this is something that we're going to go over in a lot more detail with respect to time-varying predictors. This is like your first taste of it, because this is just time. If I start out with age minus age at baseline, right, then I am deliberately, like manually removing all of that between person variance from the variable. I'm stripping it off, right? Alternatively, if I have age and then I have age at baseline as two different predictors, the same result happens because of partialing in the sense of collinearity. All of these fixed slopes are unique effects, right? It's the slope of that variable controlling for all other predictors in the model. All linear models work that way. So if I look at what age that's time varying brings to the table uniquely after controlling for between person differences in age at time 1, what's left? If I control for the between part by putting that in as a separate slope, what's left for it to do is the within part. So either I start out with, I only have the within part because I set up the variable that way, or I'm left with only the within part because I set up the model that way. And you can literally get from one to the other. The intercept will be the same. The fixed slope of the within person, whether it's time or age, even though it's a different variable, will be the same. That's what's so confusing. It's a different variable going in at level 1, but you get the same result. And then the same variable goes in at level 2, age at time 1, but you get a different result. It's nuts. You get what's either known as a contextual effect or a between effect. Contextual is after controlling for level 1, between is not after controlling for level 1. So what is the full effect of age versus what is the effect of age after controlling for time varying age? Those are two different things, but they're linear combinations. You get one or the other in each of these models, and you can add or subtract to get to the other one. So long as you don't have a random slope, these models are likelihood equivalent. What if I have crazy interactions? Likelihood equivalent. What if I have even more crazy interactions? Likelihood equivalent. So this is chapter 10, where I worked through all the math to rearrange these things to make them into each other. I must have been really upset to do this much algebra, because that is not something I would typically try to do. I'm not good at it, and I don't have the patience for it. I used to be good at it, but then I quit taking math classes because I was going to be a psych major. Big mistake. So yeah, the point of the story here is you can have age or you can have time, and as long as you have enough of the higher order terms to make them, you can figure out what the one term from one model would be based on the other model and solve it. And the example that I have for you does this with code and data. But that will have to wait till next time. So this is going to be my take-home message is avoid all of the overlapping cohort question. Just put in time. Then you can't be wrong because you're not making any assumptions about how people align themselves onto the same trajectory. You're not trying to align them. All right, 143, questions before we put pause on this and pick it up next time. I don't want to end on algebra. We'll end on words. There we go. Are you overwhelmed? A little bit. Yeah, the take home is just do time. Like that, seriously, because you can't get it wrong.
So what is in the example you provided earlier about taking different observations from different people in the same country
Mhm.
over time. What is our time in study? Or is that not going to save us?
So back to the question about different people sampled over time from the same sampling unit. In that case, I don't think there's any way to salvage that unless you're just willing to believe that they're the same people, like the same kind of people, because you lack any information to test otherwise. You just really have to believe that it's the same country or company, even though it's different people each time that are answering the questions. That also would mean that if you're trying to predict like a country level outcome, for instance, you would have to aggregate over the people. It would be like the mean whatever at occasion 0 and the mean whatever at occasion 1 to predict that country level outcome, because there's no individual level outcomes to predict. So you'd have to bring everything up a level anyway, if that's the way that you're looking at it. Yep. All right. 1:45. That means I shut up now. Thanks for being here, folks. I will see everybody on Thursday. Bye, Zoomers. Bye, Roomers.
Lisa,